Hi everybody, we are the undergraduate student team from WPI, and our project explores narrowband jamming mitigation techniques for LTE networks.
Hello, everyone. My name is Matt Farah, and I'm a current senior at WPI. I will be pursuing my master's next year as well. This past year, I worked alongside Julian, Yaya, and Cynthia on developing the LTE testbed, and then eventually we split off into two teams. And on the second team, it was me and Julian, and we helped develop the security protocols into the testbed.
Hi everybody, my name is Julian Taya and I worked on this project for my senior capstone project. I worked with Yaya, Cynthia, and Matt to develop the OAI LTE network, and then once we split off into two teams, I worked with Matt to develop a method for bypassing jamming.
Hi, my name is Cynthia Tan and I graduated from WPI in December of 2019. I worked on this project as a capstone project during the first semester of my senior year. I worked along with Yaya Brown to develop the frequency hopping jammer.
Hi, I'm Yaya Brown. I'm currently a graduate student at WPI. However, I worked on this project for my senior capstone project. I mainly implemented the frequency hopper jammer along with Cynthia.
The motivation behind our project stems from the significance of LTE in our society. Worldwide, there are currently over 5 billion smartphone users, which equates to over 60% of the global population. In addition to commercial use, the U.S. military uses LTE networks as a means of keeping soldiers on land, sea, and air all connected. LTE's technology is widely known, which also makes it increasingly vulnerable to jamming attacks. A study done by Jeff Reed and Mark Lichtman describes how the control instructions make the network so vulnerable when they are targeted with high-power noise transmission. They claim that a laptop and a software-defined radio, which can cost as little as $650, is sufficient to create this disturbance. Our projects seek to mitigate these security threats, as there has been very little research done on this topic. Here's a conceptual flow diagram of our testbed. We used a USERP B210 as our base station and a Samsung S4 phone as our user equipment because it is compatible with LTE technology. A USERP N210 was used as the frequency hopping jammer, and the jamming detector was a USERP X310. As you can see in the figure, the jammer is specifically targeting the downlink signal, and so that is what was monitored for this project. Here's a picture of our actual hardware setup inside of a Faraday cage. We used a Faraday cage to block any signals from leaving and to make sure we didn't interfere with any licensed frequency bands. We used a spectrum analyzer, shown in the top left, to verify that the signals we were transmitting behaved as expected. At a high level, a 4G LTE network consists of three main components, which are the eNode B, the UE, and the Evolved Packet Core, or EPC. The EPC is responsible for the connection to the internet and includes the Mobility Management Entity, or MME, the Home Subscriber Server, or HSS, the Serving Gateway, or SGW, and the Packet Data Network Gateway, or PGW. These are needed for the eNode B and UE to recognize each other and establish an internet connection. We implemented these using OpenAir Interface, which is an open source software platform that includes a GitHub repository to develop all the components required to completely set up an LTE testbed. We will now demonstrate how we ran the EPC and eNode B in the Linux command terminal. Running the EPC requires us to type in run commands for the HSS, MME, and gateway components separately. The HSS is a central database that stores user profiles, and the MME provides user authentication. Running the gateways is the final step for internet access for the UE. After this was complete, we then entered the run command for the eNode B, which used the LTE Band 7 configuration file. This made the base station transmit the downlink signal at the 2.68 GHz center frequency. The MME statistics show the connected components, and this verified that both the eNode B and UE were successfully connected. So once we successfully established this connection, we made sure to verify that the Samsung S4 could actually browse the internet. As you can see here, the 4G icon is displayed on the phone with an upwards and downwards arrow. This signifies that the uplink and downlink signals are being transmitted and received properly. Right now, we demonstrate a YouTube video successfully loading with our own personal OAI LTE network. After we implemented and verified the functionality of our testbed, we introduced the jammer into the system. The video is currently playing, but when we exited and tried to load it again, as seen here, The connection is clearly disrupted and there is a denial of service. When we analyzed the jammer through a spectrogram and an FFT plot, we could see how it changed frequencies unpredictably. It transmitted at a high power and randomly hopped between 2.675 and 2.685 GHz. Understanding this behavior allowed us to determine an approach for anti-jamming. This video will now demonstrate our entire testbed.
First, in the bottom right corner, that's our base station running. You have our MME, HSS, and gateway part of the EPC. Right now, we're going to demonstrate running our anti-jamming script. You just run the Python, and as there's no jamming going on right now, so nothing's going to be displayed. Now, when we run our jamming, this is just the spectrogram and the data from our anti-jamming network. Hold on, this is when we run our frequency hopper jamming. As you can see, you gotta make this a little bigger. As you can see, it is jamming that frequency in the center around 2.682, and it'll continue doing random frequency hopping. As you also can see on the our anti-jamming graphs, that you can see the jamming occurring with these red spikes at 2682, 2678 now, and you can also see that in the spectrogram below.
These spikes allowed us to determine in real time the presence of a jammer, and we will explain in the next few figures how our system reacted once it detected jamming. This is the command terminal that we ran our anti-jamming script in. Our algorithm continuously checked to see if any power levels were over a certain threshold. The phrase jamming occurring notified the user that a jamming signal was detected. Once this was determined, the Python script sent a socket containing a new downlink frequency value to the OAI server. This allowed the eNodeB to hop frequencies and bypass jamming. After this was completed, it outputted send, telling the user that it successfully switched frequencies. This screenshot was taken after jamming was detected and the eNodeB hopped downlink frequencies. It shows the X310 receiving at a new center frequency of 2.64 GHz, which is still in LTE band 7. As you can see, the figure displays a normal LTE downlink signal, and there are no longer any jamming signals interfering with the transmission. This verifies that our system could successfully evade the narrowband jammer. In order to implement this jamming detection approach, we used GNU Radio to create a flow graph to monitor the downlink frequency and then modified the generated Python script to behave as we wanted. This GNU Radio flow graph implemented a 1024-point FFT with 9.765 kHz wide bins. These were searched through by probing the results, which returned the power levels at each bin. The first block, stream to vector, was used to concatenate all the IQ data into one vector, which was then provided as an input to the FFT block. The FFT output was fed into the complex to magnitude squared block, which was then fed into the log10 block to compute the power of the signal. This value was then probed at a rate of 10 Hz for our script to process. This conceptual flow graph shows our overall approach. We begin by monitoring the center frequency of 2.68 GHz, but this changes once the jammer is detected. The X310 always receives at the same frequency that the eNodeB transmits the downlink signal. The script is constantly checking for any interference and notifies the base station whenever necessary. To evaluate the effectiveness of our anti-jamming method, we used Wireshark to analyze the packet receiving rate for the Samsung S4. This figure shows the packet receiving rate versus time for an undisturbed connection between the base station and the UE. As you can see, the values are very high, indicating that it is a high-speed system. The red line indicates when the jammer was turned on. This next figure shows the packet receiving rate for the Samsung S4 once it reconnected to the base station after it changed the downlink frequency to bypass jamming. The packet receiving rate is shown to remain above 0, indicating the packets are still being received and there is still an LTE connection. Thus, the jammer was successfully evaded. This final plot shows the packet receiving rate when the jammer began transmitting and the jamming detector was not turned on. In just a few seconds, the packet receiving rate is shown to decrease to 0, signifying a denial of service for the LTE network. This project utilized an LTE testbed and a narrowband jammer to investigate the effectiveness of an SDR for the detection of jamming. The use of OAI software allowed for the development of an LTE network that consisted of an eNode B and a UE with access to the internet. Using an XG10 was a reliable hardware component for fast and continuous jamming detection. GNU Radio is an efficient tool to monitor signals and perform computations on them. By implementing a flow graph and modifying the generated Python script, this project was able to achieve real-time jamming detection. Throughout this project, our team learned a lot. All of us came into this without having any experience with LTE networks, and only half of the team members worked with SDRs before. We are glad to have done this project as a senior capstone requirement, and the Beyond 5G competition provides us with a great outlet to present our work. Because of our limited experience, we ran into many issues with the implementation of the OAI testbed. We did a lot of literature review and found online help from a guide on using OAI made by Chance Tarver. We believe this project presents many opportunities for future work. For instance, introducing multiple eNode Bs to the LTE network would complicate our system, as the jamming detector would need to notify the correct one. Moreover, investigating security on a 5G network would be important with the new generation of cellular technology. Implementing this approach on a G-Node B may require a different approach, and this can be further explored using OAI. This project would not have been successful without all the help and resources received from many members of WPI, the Wright Brothers Institute, National Instruments, and the Air Force Research Lab. We want to thank Professor Wiglinski, our faculty advisor, for his guidance throughout the project. We want to thank Kuldeep Gill, a PhD student working under Professor Wiglinski, for all the time he dedicated in helping us with the many issues we faced along the way. We would also like to give our appreciation to Steve and Harry from the AFRL for helping us in the participation of the Beyond 5G competition, and National Instruments for providing the team with multiple SDRs. Finally, we would like to thank Bob Lee from the Wright Brothers Institute for his role in the competition. Participating in this was a great and unique opportunity, and we really appreciate getting the chance to have our senior project be selected for this competition.